Welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a pre-calculus lecture. I hope you enjoy it. This is the beginning of chapter 3, which is on exponential and logarithmic functions. Specifically, 3.1 is on exponential functions and their graphs. All right. So first, let's define what we mean when we're saying exponential functions. All right. So the exponential function of, or the exponential function f with base a is denoted as f of x is equal to a to the x, where in here a is strictly greater than 0 and not equal to 1. All right, so it's a positive value, it's a positive real number that is not equal to 1. And in here, x is any real number. By the way, essentially this tells us that the domain is that x is any real number, all right? Because x here is our variable, right? And in here, a is our base. Now, we have two basic ways that this function may look like, all right? So I'm going to draw them both on the same graph, and then I'll give key concepts about it. So let's say, all right, there we go. Here in blue, we're going to look at the scenario where a is greater than 1, all right? And in yellow, we're going to look at the scenario where a is between 1 and 0, right? Because it has to be greater than 0, but it cannot be 1. So the two scenarios are, well, you're between 0 and 1, or you're above 1, right? Now, in both of these cases, well, we already know what the domain is. The domain is all real numbers. So I'll go ahead and write that here. Domain, well, let's do it this way. Domain is all real numbers from negative infinity to infinity, which is going to be the same case for this, negative infinity to infinity. The range for both of them is going to be from 0 to infinity. All right. And I'm going to do that one in yellow. All right. Now, what do they actually look like? Well, this is what they look like. Here, in blue, it looks something like that. And over here in yellow, for when a is between 0 and 1, it looks something like this. All right. Now, in a couple of more things that they have in common here. They both have the same horizontal asymptote, the line y equals 0. They both have the same y-intercept, which is the point 0, 1. All right, that's this point right here. 0, 1, and it exists for both. And again, they both have the same horizontal asymptote. I'll just label that in red here. Now, what is different about them, though? Let's see. In here, on the blue one, from left to right, it is going up. So it is an increasing function. It is increasing. However, over here in yellow, this is going downwards. So this is actually going to be a decreasing function. So that's the very first real part where they're different. I mean, we knew visually that they were different, but why? Because one is increasing, one is decreasing. That's what we would say mathematically. Now, let's look at some examples of these kinds of functions. All right. So we're gonna look at we're gonna do a few of these. So we're gonna look at f of x being equal to 2 to the x. We're gonna look at g of x being equal to 2 to the negative x. We're gonna look at h of x being equal to 4 to the x. And lastly, we'll be looking at, let's see, what is this color different enough? Nah. Let's do something like this. Let's see. K of x is equal to 4 to the negative x. All right. So I'm gonna graph every single one of these. All right. So that we have a good idea. But before we do that, let's create a table of values. So we're gonna plug in the same values for all of them. So let's say that I'm gonna plug in -2, -1, 0, 1, and 2, just so we can create a table for all of these. And for f of x, well, what do we get? We get, plug in -2, 2 to the -2 is 1/4. Plug in -1, 2 to the -1 is 1/2. Plug in 0, 2 to the 0 is 1. Plug in 1, 2 to the 1 is 2. Plug in 2, 2 to the 2 is 4. Now let's look at g of x. And in here, we're plugging them into 2 to the -x, right? So -2, so 2 to the -2, so we end up with 2 to the +2, it's 4. Plug in -1, 2 to the -1, so 2 to the +1 is 2. Plug in 0, 2 to the 0 is 1. Plug in 1, 2 to the -1 is 1/2. Plug in 2, 2 to the -2 is 1/4. I'm going to start looking at the pattern here. Let's look at h of x. When we plug in -2, 4 to the -2 is going to be, well, 1/4 squared, which is 1/16. Plug in -1. 4 to the -1 is 1/4. Plug in 0. 4 to the 0 is 1. Plug in 1. 4 to the 1 is 4. Plug in 2. 4 to the 2 is 16. Now let's look at our last friend over here, k of x. And that's not the right color. There we go. So plug in -2, 4 to the -2 is 4 squared, which is 16. Plug in -1, 4 to the -1 is just 4. Plug in 0, 4 to the 0 is 1. Plug in 1, 4 to the -1 is 1/4. And plug in 2, 4 to the -2 is 1/16. So you'll probably notice by now that there's kind of a pattern going on between these two as well as these two, right? Which you should have been noticing, which is good. But now let's look at graphically what these are doing. All right. So let me draw my graph, and I'm gonna try to do this semi-accurately, just so that we have a better idea of what's going on. And so 1, 2, 3, 4, 5, 6, 7, 8. Counting. Right, that's good enough. And over here is 3. All right. So if I look at this blue column, right, 4 2 to the x, well, one thing I want you to notice for all of them is they're both going to the point 1. All right, so they're all going to have the same y-intercept. All right, and when I plug in 1 in here, well, we had the point 1, 2, then we had the point 2, 4. If we had kept going, we would have had 3, 8, right? Because we would have had 2 to the third, which is 8. And then over here we had 1/2, 1/4. We would have had 1/8. So we have something like this happening here. All right. So that adds that first column. The next one, we're gonna have here. Well, when I plug in 0, we still have the point of 1. When we plug the -1, we had 2. When we plug in -2, we had 4. -3, we had 8. So on and so forth. And in here, we end up with this. All right. Notice that this is an exact mirror image, or as close as possible according to my drawing, of the blue one, which should make sense. It should make sense. How come? Because, well, in here, g of x is equal to f of -x. And if you think about transformations, right, what's happening here when I plug in -x into a parent function, and here the parent function being 2 to the x, and I'm plugging -x into it, well, it's going to be just a mirror image. All right. Now in here, you can also think of this as being 1/2 to the x, right? And now that's important because now it fits exactly what we're doing over here with a being our base being between 0 and 1. All right. So in here, that 1/2 is between 0 and 1, but it's equivalent to just being a transformation where we reflect over the y-axis. That you will also see here, because this is also going to be just 1/4 to the x. All right, so we're going to have a reflection over the y-axis for these two, and it's still going to be a decreasing function, right? So let's see what these look like. So I guess I'll do the green one first. So we have the 2 to the 1, we have 1 to the 1/4, and 1/4 is less than 1/2. So 1 to the 1/16, which is much smaller there, and smaller and smaller. Then we plug in -1, we had 4. We plug in -2, technically we had 16, which would have been all the way up here, I guess. And we have something like this. Notice how quickly that grew, but it's still overall in the same shape, right? So in yellow, we're going to have the mirror image of that, right? So we have 1/4, 1/16, and even smaller values. So, and then 1/4, 2/16, which would be technically all the way up there. So something like this. So that's a 2/4, or 1/4, excuse me. And then the rest. So a few things I want you to notice here. Well, yes, I already said the reflections, right? But also, let's look at f and h, all right? The bases of 2 to the x and 4 to the x. This base of 4 is bigger than 2, right? And what you'll notice is that it went up much faster, all right, than the 2 to the x. Similarly over here, between g and k, our base of 4 is larger, so it grows faster as we go towards -infinity than our function g. Every single one of these has the same horizontal asymptote down here of y equals 0. And that's because the only transformation that really happened anywhere at all was here with that -x, but we didn't do any shifting, all right? So now, when we go to actually sketch some, we're not going to be, I don't expect you to do everything that I just did here. So let's talk about how to actually sketch these, all right? That was just to give you an idea of what is going on with them in general. But before we do, I do want to talk about something called the one-to-one property. All right, and this is for all exponential expressions. So for a being greater than 0 and not equal to 1, a to the x is equal to a to the y if and only if x is equal to y. All right. All right. That will come into play as we sketch some of these. So let's go ahead and sketch. And we're going to start with f of x is equal to d to the x. Let's do minus 9. All right. So what I want you to do when you go about sketching these is I want you to think of this in terms of transformations. All right. What are the transformations happening here from the parent function? And first, well, we need to decide what is the parent function. The parent function is just 3 to the x. So what does 3 to the x look like? Well, let's look at it this way. 3 to the x is, well, our base is 3. So it looks something like this, where it crosses at the point 0, 1, right? And we have a horizontal asymptote of y equals 0. So now, what is this going to do? Well, we don't have just 3 to the x, we have 3 to the x minus 9. That minus 9 is bringing down everything down by 9, including the horizontal asymptote. So what we have here is that the horizontal asymptote is a line y equals negative 9 because everything needs to be shifted down by 9, right? What else needs to be shifted down? Well, our y-intercept. Our y-intercept needs to be shifted down by 9 units. So that implies also that our y-intercept is going to be the point 0, negative 8, right? Because what I'm doing is bringing down this point down by 9 units, excuse me. So what does that look like? Well, let's see. We're going to have, let's draw that better. We have a horizontal asymptote of y equals negative 9. So let's say something like this. Oh, let's fix that. So this is a horizontal asymptote of y is equal to negative 9. And we need to cross now at 0, negative 8. So 0, negative 8 would be right before that. So 0, negative 8. And then we know it needs to make this shape. All right. So it needs to make that shape. But now the question is, where is it crossing? Right here. What point is that? Because we like to label all of our intercepts. Well, that's our x-intercept, right? And how do we find the x-intercept? The x-intercept is when y is equal to 0. So, but what I'm going to say here is we're going to have 3 to the x minus 9 is equal to 0, which means 3 to the x is equal to 9. But now, from the one-to-one property that we just learned, the only possible way that these are equal to each other is if we have the same exponents, right? How does that help here? Well, in here, we can rewrite this as 3 to the x is equal to 3 squared, right? Because 9 is just 3 squared, which then tells us that x is equal to 2. So what we found here is that our x-intercept is the point 2, 0. So that's this point right here, 2, 0. And there you go. We did this by transformations and also by just knowing some facts about our intercepts. Let's do another one. All right, let's do another one. So let's say that I had something like f of x is equal to 5 to the negative x plus 1. All right. So what is that going to look like? Well, we can do this in two ways. Either think of this as the parent function of y equals to 5 to the x, right? And in here, well, what would that look like? That would look like this. Or we could think of it as a parent function of y equals 1/5 to the x, because we could just rewrite this as 1/5 to the x plus 1, right? So what would that look like here? Well, this parent function will be facing the other way. Now, in general, I'm going to stay away from looking at it this way. I'm always going to look at it this way, with the parent function being where the base is greater than 1, all right? Because we can just think about that transformation as being a reflection, right? So we can say here, well, that negative x, that's going to be a reflection over the y-axis. And this positive 1 is going to be moving everything upwards by 1 unit, including a horizontal asymptote, right? And here we have a horizontal asymptote of y equals 0. So this, everything's being shifted up by 1. So our horizontal asymptote is going to be the line y equals 1. It also moves our y-intercept. Our new y-intercept is going to be 0, 2, right? Because everything's being shifted up by 1. This point right here is 0, 1. So what does that look like? Well, let's see. And we're gonna draw this up. So we're gonna start with our horizontal asymptote. We said it's line y equals 1 now. So in here, this is line y equals 1. We have a y-intercept of 0, 2. Y-intercept of 0, 2. And then it needs to follow this general shape. So it needs to follow that general shape. And there we go. That is the sketch of that. This point right here being 0, 2. Notice in here we didn't look for our next intercept. All right. And we shouldn't have one, right? Because what we're doing is shifting things, this thing upwards. This thing that didn't have any x-intercepts upwards, so it still shouldn't have any x-intercepts. All right, let's do. Oh, hold on. I forgot to do the reflection. Look at that. That's awful. Let's fix this. So I didn't do the reflection, so we have to reflect it. There we go. Something like that. And let's get rid of all the bad stuff. All right, all fixed. Much better. Good job catching my mistake, if you caught it. Now, it's fixed though. Let's do another one. Let's say that I have f of x is equal to, I did 3 already. 2 to the x minus 1 plus 4. All right. So now in here, what are we going to do here? And actually, first of all, I'm going to change that plus to a minus. 2 to the x minus 1, 2 to the x minus 1 minus 4. There we go. All right, so the first thing I'm going to say is, well, what is the parent function that we're looking at here? The parent function is 2 to the x, which we know looks like this, with the point 0, 1, and the horizontal asymptote of y equals 0. All right, so this is what I want you to always think about. Now, what transformations are happening here? Well, this x minus 1, well, it's happening inside of the x. If you recall from transformations, that meant it's moving to the right by 1. This minus 4 is moving everything down by 4. All right. So what does that mean? Well, since everything's being moved down by 4, that tells us that the horizontal asymptote is the line y equals negative 4, right? What else do we know? We know that the y-intercept, well, it's moving down by 4, so 1 minus 4 is negative 3. And then it's also moving to the right by 1, so 0 plus 1 is 1. So this point 0, 1 is now going to be at 1, negative 3. All right, so let's see what that looks like. So let's do it this way, right? So we have a horizontal asymptote of y equals -4, and that would look something like this. Y equals -4 being a horizontal asymptote, and then we're moving things to the right by 1 and down by 4. So this point of 1, -3 exists somewhere on the graph. So 1, let's say here's 1, and here's -3. So we have this point on there. And then from there, well, we know that that's this point and it needs to look like that. So it's going to look something like this. Right? Now, a few things. What are the points that are here? Right? Because we need to figure out our y-intercept and our x-intercept. Notice I'm changing that. This should say quote-unquote y-intercept because it's being shifted. Our real y-intercept is when x is equal to 0. So we're looking for f of 0. So that's going to be 2 to the -1 minus 4, right? 2 to the -1 is just 1/2. So 1/2 minus 4 is -3/2, otherwise known as -7/2. So this point right here is the point 0, -7/2. This point over here, that's our x-intercept, which is when y is equal to 0, right? So what does that do for us? So we have 2 to the x minus 1 minus 4 is equal to 0. Move the 4 over. 2 to the x minus 1 is equal to 4. 4 is the same thing as saying 2 squared, so we have 2 to the x minus 1 is equal to 2 squared. From the 1-to-1 property, this tells us that x minus 1 is equal to 2. And consequently, x is equal to 3 is our y-intercept. So this right here gives me our x-intercept. So this point right here is 3. And it's not drawn exactly to scale, but it looks something like that. So it's really the 0.30. Alright. So it's really just a matter of how does the transformations affect the asymptotes and the intercepts. Alright. Now notice again in here, and I should have put these quotes earlier on, because I'm just saying the original y-intercept, where does it move to? Alright, it's not necessarily saying that this is going to be the y-intercept. Of course it's not, because the x value would have to be 0. Now, so in general, that's really all you have to do. You just have to look at what transformations are happening. Alright. Now, let's talk about a very important number. The natural number, e. And in here, when I'm saying natural number, I should be saying the capital N, natural. Let's rewrite that better. Let's rewrite. Okay. The natural number e. Now, e is approximately equal to 2.71828182845 and the only pattern that really repeats there is that 1828 1828 at the beginning, but after that it doesn't repeat. All right, in here e is irrational. All right, it's an irrational number. Recall that meant that it is not a rational number, which really means, well, cannot be written as a ratio. All right, because remember, rational means it can be written as a ratio. So e is irrational, so it cannot be written as a ratio. In other words, it cannot be written as a fraction at all. All right. In here, we care about e for a lot of reasons, but in here, e to the x, this is the exponential function with base e. And you would have a calculator for that e. You have a button on your calculator for that e. All right. It should look like something as e to the little box. All right, or something like just e by itself, the letter. All right. But every scientific calculator has a button for that number e. So if you were to plug into the calculator the following values, so for example, if I did f of -2, well, we would write it as e to the -2 or e to the or 1 over e squared, right? And in terms of math, we'll be done. But because we have calculators, we can rewrite this as this is approximately, and that's not the approximately symbol. There we go. This is approximately 0.13533353. All right. You could do things like f of -1, which would be 1 over e, right? E to the -1. And that is approximately 0.367828. Wait, hold on. 78794 and other stuff. All right. And now, what does the graph of e to the x look like? Well, the important part to realize there is that e is bigger than 1. All right. In fact, it's also bigger than 2, but not as big as 3. Why do we care about that? Well, let's think of it this way. If we were to graph 2 to the x, so here in yellow, we're going to do y equals 2 to the x. 2 to the x will look something like this. All right. And then if I were to graph y equals 3 to the x, well, 3 to the x, it's going to rise a little faster, but it's also going to fall a little faster. So it's going to be below this way. Let's draw that better. Something like this. All right. But now, e is between 2 and 3. So if I look at y equals f of x equals e to the x, well, it's going to rise faster than 2 to the x, but not as fast as 3 to the x. So it's going to be somewhere in here, right? And in there. And again, all of these will be crossing to the point 0, 1. But essentially here in the middle one, that's e to the x. Now, we'll talk about some applications of e to the x, but now I want to talk about something that might seem unrelated to this right now, but you will see how it is related to us. So first, let's talk about simple interest. All right. And you may remember the formula for simple interest. It is I is equal to PRT. All right. In here, where I is interest, that is interest earned. P is the principal. R is the rate as a percentage. All right. And T is the time. All right. And this has to be in years. Now, if we let T be equal to 1, all right. So let's just consider what happens over 1 year. Over 1 year, the interest is going to be just I is equal to PR. All right. Now, at this point, what we're going to say, well, let's look at this table. Let's look at how we can compound all this interest. So we're going to talk about compounded interest, and it's going to be based off here. compounded interest. And we're going to look at a year. So we're going to start looking at years like a year 0, year 1, year 2, year 3. And then we're going to look over here at what the balance is after compounding. So balance after compounding. All right. So let's say that you start with some amount. All right. Your original amount in there is just going to be strictly your principal, right? Now, that's at year 0. At year 1, at the end of the year 1, the amount in year 1, the amount that you will have in an account. So here we're talking about like just any account that earns any kind of interest, right? So the amount that you have in the account is, well, your original amount, P, right? That's what you had at the beginning of the year, plus the interest earned. Now, the interest earned throughout the year was just PR. So what we have here is really just, if I factor out a P, I have P times 1 plus R. All right. Now, that was at the end of year 1, right? At the beginning of the year. So in here, if we're looking at this timeline, right, going this way, here, I put the balance in there. I put my principal in there. Here, it is the end of the first year. We're going through time. That's where we are. Now, over here, at the end of the second year, the amount at the end of the second year, well, we're going to have the original amount that we had at the end of the first year, plus the interest earned on that amount. The interest earned on that amount is just A sub 1 times R, because, well, at the beginning here, the amount was A sub 1, right? And then we earned interest throughout the year on that amount. That's what this is doing. Now this, I see that there's an A sub 1 in both of them, so I can factor in A sub 1. I'm left with 1 plus R. But A sub 1 was P times 1 plus R. So we have P times 1 plus R times 1 plus R. So P times 1 plus R squared. So again, in here, we have just the original amount. And here at the end, we have A sub 1, A sub 2. Now let's look at the end of A sub 3 in that year, in the year 3. What is that going to be? Well, in here, we would have had the original amount at the beginning of year 2. So we're going to have that original amount, like whatever we had at the end of year 2, right? At the end of year 2, plus whatever interest we earned throughout that entire next year. The interest that we earned throughout that entire next year is going to be A sub 2 times the rate of interest that you earned. So in here it's going to be A sub 2 is equal to, A sub 2 times 1 plus R, because I can factor out the A sub 2. And well, A sub 2 was P times 1 plus R squared, but then we have that times 1 plus R, so P times 1 plus R cubed. And as time goes on, well, this pattern continues, right? So if I look at just some generic time t, our A sub t is going to be, well, essentially A sub t minus 1 plus A sub t minus 1 times R. We're going to be able to factor out that A sub t minus 1 times 1 plus R, right? And, well, long story short, we have P times 1 plus R to the T, all right? So now, what did we actually do here? So in here, we were earning simple interest year after year, all right? And we were just compounding things once a year. So if we accommodate for frequency, so accommodating for frequency, we end up with the following. So A is equal to P times 1 plus R over N to the NT. And what do we mean by the frequency here? In here, this N is number of compoundings per year. And what do we mean by that? Well, for example, if it's quarterly, that's supposed to say quarterly. N equals 4. If it's monthly, N equals 12. So on and so forth. All right. But essentially, that's what that does for us. Now, so we're accommodating this format into here for the number of compoundings per year. Now, let's manipulate this. So in here, I'm gonna say let M equal to N over R. Now, this implies two things. One, this tells us that 1 over M is equal to R over N. And I care about that because it's right here. But it also tells me that N is equal to M times R. All right? Why do I care about that? Well, because now this line right here is going to say A is equal to P times 1 plus, well, R over N is 1 over M. And this N is MR. And then we still have this T. Now from rules of exponents, I can apply this parentheses here without affecting anything. All right, those parentheses there, or those blue brackets, are not doing anything. So let's look at just that piece on its own. All right. So 1 plus 1 over M to the M. All right. Now in here, well, what we're gonna say is, what if M starts getting bigger? All right. What happens to this 1 plus 1 over M to the M? Well, I'll tell you what happens. When M is equal to 1, you just get a simple answer, 2, right? 1 over 1 is 1, 1 plus 1 is 2, 2 to the 1 is just 2. When M is equal to 10, and plug in this into the calculator, 1 plus 1/10 to the 10th, we end up with this value. 2.59374246. When we plug in 1,000, we end up with 2.716923932. When I plug in 100,000, I end up with 2.71826. 1828 0469. Sorry, that was for 1 million, not for 100,000. So let's shift that. That's gonna be for 1 million. For 100,000 though, it was 2.718268237. And then for 10 million, we have 2.718281693. What I want you to notice here is that as M goes to infinity, these values are going to the value E. They're getting closer and closer to E. All right? Because remember, E was 2.718281828.459, which I hope with a whole bunch of other stuff. But that's already pretty close to E, right? 1828169. That's pretty close. So now, why is that important? Well, that was just this piece right here, right? Which leads me to the big point here, that, well, if M is getting bigger, well, what's really happening overall? Well, if M is getting bigger, well, that means that this fraction right here is pretty big, right? But R is just some fixed rate, right? The interest rate. So really, to make this fraction bigger, well, the real possibility here is that n has to be getting bigger. So the number of compoundings are getting bigger and bigger per year. All right. So what this essentially tells us now is that as we compound more and more frequently, we get that A is equal to PE to the RT. And in fact, this is for continuous compounding. All right. A equals PE to the RT. So now we have two formulas for compounding. We have the simple interest one, the compounded interest one, and the continuous compounding. So let me go ahead and write those formulas. So formulas for compounded interest. And they are as follows. So for n compoundings per year, we use A is equal to P times 1 plus R over N to the NT, where T is in years, N is the number of compoundings, and R is a percentage, the interest rate. For infinite compoundings per year or for continuous compounding, we get A is equal to PE to the RT. All right. So now let's do an example with this. And I'm just going to do a word problem. Let's say you invest $6,000 at an annual rate of 4%. All right, so that's our interest rate. Find the balance after 7 years when interest is compounded in the following ways. First, we're going to look at it as quarterly. Then we're going to look at it as monthly. And finally, we're going to look at it as continuously. All right. So, well, what does this actually tell us? It tells us a few things. If we're investing $6,000, that is our principal. Our rate is here. So that's our rate, but that's going to be as a decimal, it will be 0.04. And then in here, we still have, or we have this also, this value of t for years, right? Our t is 7 because it's 7 years. Now, in each of these scenarios, we get something differently. For quarterly, n is equal to 4. For monthly, n is equal to 12, right? So that's when we're compounding 4 times a year. Here we're compounding 12 times a year. But for continuously, we're compounding infinitely many times a year. So we're going to have to use a different formula for that one. Now, in here, let's do the first one. If we're doing quarterly, well, we have that the amount is going to be P times 1 plus R over N to the NT, right? Always write down your formula. And it's going to be, well, our principal is 6,000 times 1 plus R, our rate is 0.04 over N, and here N is 4, and that to the 4 times 7, right? N is 4, T is 7. If you plug this into the calculator, we end up with something like $7,927.75. So after 7 years, if you compound it 4 times per year, we end up with that much, $7,927.75. Now, what if we do it monthly in the second scenario? Well, you might imagine that if we're going to be compounding more often, things change, right? And in fact, they do, because now we're compounding 12 times per year instead of 4 times per year. And when we plug this into the calculator, we would see that we get $7,935.08. Notice that more compoundings gave us essentially more money, right? Now, let's look at this continuously compounding. So essentially, we're compounding infinitely many times per year. All right, well, because we're compounding infinitely many times per year, or continuous compounding, we need to look at a different formula. A equals PE to the RT. And in here, that's going to be just 6,000 times E to the R. The value of R was 0.04 times T, which was 7. So plugging this into the calculator, you get $7,938.78. So what does this really tell us? Well, it tells us that compounding more often yields more money, right? But not so much that you can just get rid of it, that you can just get rich off of compounding, because I mean, look at that. Compounding infinitely many times, it only went up by $3 more, right? But over here, when we went from 4 times to 12 times, it went up by what? What is that? $7, $8 to go from here to here. So, yeah. So that's the story there. Now, that is the end of 3.1.
Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.